This is the most famous curve in all of science. The bell curve. It shows up in test scores, in measurement errors, in the stock market, in quantum physics. And hiding inside it is one of the strangest results in mathematics. The exact area under this curve is the square root of pi. Not roughly, not approximately, exactly the square root of pi. But here's the twist. If you try to compute this area the way you learned in calculus class, you can't. It's impossible. Let me show you why, and the genius trick that cracks it. Here's our function, e to the negative x squared. To find the area under it, calculus says, find the antiderivative, then evaluate it at the endpoints. So, what is the antiderivative of e to the negative x squared? Try it. Substitution fails. The chain rule demands an extra factor of x that just isn't there. Integration by parts makes things worse. And this isn't because you're missing something clever. In the 1800s, the mathematician Joseph Liouville proved that the antiderivative of this function cannot be written down at all. Not with polynomials, not with exponentials, not with trig functions, not with logs. In the world of elementary functions, it simply does not exist. And yet the area is exactly root pi. So how can we possibly find it? Here comes one of the most audacious moves in all of mathematics. Called the mystery area I. We can't compute I directly. So instead, we compute I squared. That sounds insane. How does making the problem bigger make it easier? Watch. I squared is just the integral times itself. But the variable inside an integral is a dummy, a placeholder. So in the second copy, rename x to y. Now the two integrals merge, and the exponents combine. E to the negative x squared times e to the negative y squared is e to the negative x squared plus y squared. A product of two one-dimensional integrals just became a single two-dimensional integral over the entire plane. We've turned an area problem into a volume problem. And here's what that volume looks like. Take the bell curve and spin it around the vertical axis. You get this, a smooth, perfectly symmetric hill floating over the plane. I squared is the volume underneath it. And that symmetry is the key to everything. Look at the hill from directly above. It's a target, perfect circles rippling outward. The height doesn't care which direction you walk. It only cares how far you are from the center. So let's stop describing points by x and y, and describe them the natural way, by their distance from the center, r, and their angle, theta. In these polar coordinates, x squared plus y squared is just r squared. The function collapses to e to the negative r squared. One variable, instead of two. But here's the subtle part, the detail that makes the entire trick work. When you chop the plane into polar pieces, the pieces are not equal-sized squares. A patch far from the center is wider than a patch near it. Its area gets stretched by a factor of r. So the little piece of area, dA, becomes r, dr, d theta. That extra factor of r, that tiny piece of bookkeeping, is about to unlock everything. Because look at what we're integrating now. R times e to the negative r squared. That extra r is exactly what the chain rule was begging for all along. The antiderivative is simply negative 1/2, e to the negative r squared. The impossible integral just became a one-liner. Evaluate it from 0 to infinity, and you get 1/2. Then sweep the angle around the full circle. That multiplies by 2 pi. So I squared equals 2 pi times 1/2, which is exactly pi. I squared is pi, which means I, the area under the bell curve, is the square root of pi. There it is. Exactly. The area that calculus said was impossible to compute. And this is not just a party trick. Take this curve, divide by root pi, stretch it just right, and you get the normal distribution. The foundation of all of statistics. Every confidence interval. Every poll's margin of error. Every A/B test on the internet. They all work because this area is root pi, a circle constant, born from squaring an area and spinning it into the third dimension, quietly sits at the heart of every bell curve in the world. So the next time someone tells you an integral is impossible, maybe it's just waiting for a second dimension. If this made calculus feel a little more magical, subscribe. There's a lot more where this came from.